Okay, so in this one it says a water tank is built in the shape of a circular cone with height 5 meters and diameter 6 meters at the top. Water is being pumped into the tank at a rate of 1.6 meters cubed per minute. Find the rate at which the water level is rising when the water is 2 meters deep. Okay, so first thing let's do. So let's make a picture. Okay, so this cone, they tell us, has a height of 5 meters. And it'll be a bit more useful just to write down the radius right now, even though they gave us the diameter. So what's the radius?
3.
Yeah, 3, right? Yeah, so 3 meters. Okay, so that's the height and the radius of that cone, right? So now what's helpful for these ones is to draw a second little cone inside there, right? Because this is what's happening is the water is being poured into this thing and it's going up over time, okay? And we want to find the rate at which the water level is rising when the water is 2 meters deep. So from here to here, like when this is 2. And then in this case, I don't know what this is going to be, like that R value right there. So I'm just going to write R for a second.
Oh, that's going to be changing.
It will be, yeah, that'll be a changing value, right? Yeah. Yeah, okay. Yeah, so, all right, so let's write down what we have. So we have a height. Height is equal to 2 meters. And that one is changing, right? That thing's that's changing over time. We know dV dt is equal to what?
1.6 meters cubed per minute.
Yeah, the volume, yeah, 1.6 meters cubed per minute. And we're looking for dH dt. Okay, so let's, I just want to show you what the problem is going to be in this question. This is kind of like a specific type of question. So let's write down our equation for this. So the volume of a cone is 1/3 pi times r squared times h. All right, so nowhere in this question does it say anything about the changing rate of the radius, right, of this cone. I'm really interested in h. I'm interested in the changing rate of the height of this cone, right? So I would sure rather have this thing that it was in terms of v and h, right? And then the others were just constants. That would be nice, right? I wouldn't have to deal with like taking the derivative of this. Like I said, I'd also have to do the product rule there, which would be annoying. Yeah, can you guys think of any way that we can relate r and h together so that we can just make this equation a little different so that it's just has h in it instead of r? I'll give you a hint.
Is it a triangle?
Yeah, it's got something to do with what's happening over here, right? With our similar triangles. You guys see we have 2 triangles made here? We got this triangle. And then we have the bigger one. So we can relate those sides, right? So what I mean by that, let's make a little equation, right? So we can say r over h. Here, I shouldn't have put 2 in there. Can you guys erase that and put just h there for a second? Because that thing is changing, but we want to know when it is 2, right? But it'll be helpful just to call it h for now. So we can say that r over h would be equal to 3/5, right? Just setting those 2 ratios equal to each other. So then I can just rearrange this a little bit. That would mean that r is equal to 3/5 times h. Now, you physics people, what do you think we could do with that? Yeah, we can substitute that in, can't we? Right? Why not replace that R with this expression? So we'll write it in as V is equal to 1 over 3 pi, and then instead of an R, I'm going to be putting in (3 over 5h). I just made it red so you can see that it was the same. I just replaced the R there, right? Okay, and then we'll just clean this up a bit. So V is equal to, that ends up being, if you square it like the 3 and the 5 and then simplify, you end up getting 3 pi over 25 h cubed. Okay, that's a lot easier to take the derivative of, isn't it? So I think we're ready, right? That's about as simple as we can get. So let's take the derivative. So we'll take the derivative of, so it'll be dv dt is equal to this coefficient out front. I'm just not going to worry about that again. That's just 3 pi over 25, and then I'm just taking the derivative of h cubed. So that would be times 3h squared, and then times dh dt. That's exciting. That's the one we're looking for. Okay, so then from there, you guys kind of see where we're probably going here. Now we're just kind of plugging things in, right? Now we know dv dt, we know that value. That's 1.6.
Why did it become 3 pi over 25?
Oh, just here. That was just, if you squared 3, that'd be 9. If you squared 5, that'd be 25. And then 9 over 3 would leave you a 3 on the top and 25 on the bottom.
Oh, okay.
Yeah. Okay, so yeah. Here, you know what? Let's clean that up one more time though. So I'll say dv over dt is equal to 9 pi over 25. H squared times dh dt. Right, that would be like our equation that we can start throwing things in, right? Okay, so we know dv dt is really 1.6, right? That's the rate that the volume's changing over time. And then if I throw in, what was that? 2, right? So that's going to be 9 pi over 25 times 2 squared. Why am I throwing a 2 in there? Yeah, this is the height I'm interested in, right? I want to know what the rate of change is at that height. Yeah, so okay, so we're going to throw that 2 in now, right? Now we can do it because we know because that number was changing, but we want to know the rate of change at that particular moment, right? So now I can throw it in. And then times dh dt, and that's the thing we're looking for. Okay.
Is height cubed just because it's like
It's
just
volume.
volume?
Yeah, because it's volume. Yeah. Yeah. Okay, so this is really, here one more time. 1.6 is equal to 36 pi over 25 times dt, or no, dh dt, sorry guys, dh dt. Okay, if you just rearrange this, 1.6 times 25, and then divided by 36, we end up getting 10 over 9 pi is equal to dh dt. Okay, sorry, I'm getting kind of squished here, but if you can write on the other side here, that would also be equal to 0.4. And then what would my units be on that one? Would it be, yeah, meters per minute. This is a height.